Okay. Right, so welcome everyone to our GIScience webinar for the Royal Geographical Society with IBG. And today we have the pleasure to have Andrew Crooks, who is a professor at the University at Buffalo, at the Geography Department, and also faculty member at the Renew Institute. And his research relates to exploring, understanding, and communication, and the communication of natural and socioeconomic environments using GIS, using social network analyses, and agent-based modeling. And today is here to talk about analyzing and modeling urban environments and utilizing computational social science. And by the way, the event is being recorded, so it will be available online. And I forgot to mention that my name is Andrea Ballatore. And if you have questions, please use the chat. And normally we do the Q&A at the end of the talk. So let's welcome Andrew at our webinar. And Andrew, the floor is yours.
Thank you so much, and thank you so much for inviting me today. It's a pleasure. It's a shame that I can't actually physically be in London, really. I do miss having curries or having a drink and being able to walk to the tube and get home that way. So today I want to talk about. You can see my screen, okay? I presume.
Yes, we can see you well. Yeah.
Awesome, thank you. So today I want to talk about. Well, that's the title, but really, what I want to talk about is how. Sort of, the way I've been exploring cities over the last sort of 10 years, really, and really how we can view cities through the lens of computational social science. And so, in this talk, I want to talk about what is computational social science, and then why we might consider using CSS or computational social science to study urban environments. And one of the main methodologies, as you'll see through this talk, is that of agent-based modeling. So I didn't know what the audience was. I know there's some people in the audience, like Alison Heppenstall here in Cobus, that know quite a lot about ABM, but I just wanted to give a brief overview about what is ABM and how we can link ABM to data, and what are some of the challenges there, and potentially how new sources of information can be leveraged to really understand cities and urban environments, and give us a new lens to sort of explore these cities, and then give some examples relating to how we can use data to look at disaster relief, pedestrian movement, wildfires, evacuations, and then how all these new sorts of data are giving us this new lens and also a new understanding of how we can think about spaces and link to different spaces, and then a summary. So we'll see how we go. I promise trying to do all this in 45 minutes. So, but so we'll just go through this. So, what is computational social science? It's sort of the study of social systems or social science through computational tools, not just necessarily computational tools with respect to this simple geographical information system, but it's also leveraging other advances, as in like geographical data science now is utilizing a lot more with respect to machine learning, or say political is utilizing language processing to understand various corpuses of text. Here in computational social science, we're trying to leverage techniques developed in the computational science, in the computer science field, and apply them to social science problems. So and often in computational social science, we're building models and trying to understand interactions of various actors that make up the system of interest. So if we have the housing market, we might be interested in individuals buying and selling houses. If we're looking at traffic control, we might be looking at individual drivers or people deciding to take public transport versus driving, which during COVID is quite an interesting, potentially an interesting area. But the idea, or just the people who make up the city, the urban systems, and the idea of computational social science and model is really to gain a greater understanding of the system of interest. And if we can understand these systems in greater detail, potentially we can better manage these systems. So, for example, if we're looking at housing markets, if we understand how people buy and sell houses, and then we can see a housing bubble emerging, for example, is there something that we can do to stop that from happening? Or if we know how people are contributing to traffic jams, can we smooth out this traffic flow through, say, different management techniques, such as altering timing of traffic lights, or and so forth? So, the idea is that we study these systems through the lens of complex adaptive systems. And reason is because the idea is, the world is a complex system, and the whole is much greater than the sum of its parts. So just adding things together doesn't necessarily do this. Complex adaptive systems, these systems that adapt, changes in situations. Like, who would have thought that we would change our work lifestyle 2 years ago, like, in light of COVID? But international trade networks, pandemics, fake news, social media, all these examples are basically systems that are self-organizing and changing. So, how we see how a pandemic would spread from, say, China, then along transportation corridors, international air travel to major hubs, and then from the major hubs spread out to the rest of the world, as we see with COVID today. Or and then, there's a lot of interactions, and the aim of computational social science really is to sort of study these interactions. So how do online bots potentially impact public opinion with respect to say vaccination hesitancy? Or if you into politics, how did misinformation campaigns through these social bots impact the presidential elections that we recently had, or previous ones? Or how, by people moving to cities, is encroaching into sort of more rural areas, so the urban sprawl type of things. The idea is, can we model these complex adaptive systems from the bottom up? And my focus in this area, sort of in the urban analytics / computational social science area, with respect to cities. Why am I interested in cities? Because, for the first time in human civilization, back in 2007, I think it was, more than half the world's population were living in cities. Now, and this is only going to get more and more, grow in the coming decades. Cities are really great examples of these complex adaptive systems. They compose of many parts. They're very dynamic. There's a lot of discrete actors, all interacting in space and time. And it's the interaction of people within cities and these systems that have a large impact on many issues, such as the economy. People, like urban shrinkage. Why do people, cities are growing, but not all cities are growing? Why is, for example, Detroit shrinking in that sense? And therefore, how does that shrinkage impact, say, taxation? And therefore, if you have less tax, you have less money to spend on public services, things like that. Or changes in health, climate change, people deciding, to buy the big SUVs in America, how that impacts potentially on increases in pollution, especially if they're living further away. There's a lot of interactions within cities, which I think are fascinating to be able to study. The question is, how can we study these types of things? But as I say, cities are growing. Megacities are also sort of on the rise as well. Megacities are these cities that are over 10 million people. In 1970, there was only around 8 megacities in the world. Now we are around 36 megacities. Of course, I just want to define a city is a question, but according to the UN, there are 36 megacities in the world. And this is a map of showing you where these current megacities are. But these megacities are going to be growing. And by 2030, it's estimated that 41 cities are going to have over 10 million people inside of it. And you can sort of see this growth in cities is not equal. It's mainly in the global south. And combine these growth of mega cities and the challenges urban growth focuses on, that plus things like more people living in cities, like 6.3 billion, I think it is going to estimated by the UN by 2050. These are really dense urban environments. They're going to be home to, like, cities in general are going to be home to around 75% of the world's population. So understanding cities, the growth of cities is a real challenge. With growth also comes other challenges, especially slums, so or informal settlements, depending on how one wants to define them. Growth is not equal. Currently, the UN estimates over 1 billion people currently live in slums. That's roughly around 1 in 3 urban residents are currently living in slums around the world. It's growing. By 2030, I think the UN estimates that around 2 billion people are going to be living in slums, and potentially 3 billion people by 2050. And how can we manage these types of issues? And this slide here is really just showing you, some populations per country versus the urban population. So the blue is the total urban population, while the red is the percentage of the slum population in those cities. You can sort of see how slums are a global phenomenon. It doesn't mean areas that are white here. It doesn't mean that these areas have no slums. It means we don't have data on the slum population there. And so even characterizing what is a slum is a real challenge. And this is another area, I think, where computational social science and advances in remote sensing, machine learning could also play a big role in detecting and mapping these types of slums. And Ron Habia, a colleague from George Mason, has been leading an effort to better understand these slums over time. But in CSS and systems, we're interested in a whole range of challenges. We're interested in the micro movement of pedestrians over seconds, over to large scale migration over decades, and nearly anything in between. So through the lens of computational social science, we've been exploring a whole variety of different applications, different spatial and temporal scales. And the second part of this talk really will focus on how can we use new sources of data to better understand these systems within inside of this. So try to understand the inherent complexity of the systems, and also the social, economic, environment from an environmental perspective of these systems as we move forward. But cities are challenging, and I used to deal a lot with physicists, and physicists always said that the social sciences are easy sciences. But then I like to point out that I think that trying to understand humans and population movements, or how people react in times of crisis, is a real challenge. And these two quotes from 2 Nobel laureates in physics, and they roughly say the same thing. Imagine physics would be if electrons had feelings, or if electrons could think. And this is a challenge. People are not behaved like in the physical sciences. So I think the challenge is trying to understand people in these systems. And this is sort of the thing that doesn't keep me up at night. Nothing really keeps me up at night these days. But it does make me think a lot. Is how can we better manage or better model human behavior within these systems, within the world? Because as Alan Wilson wrote back in 2000 in his book on complexity in cities, human behavior cannot be understood or predicted in the same way as in the physical sciences. There's a lot of emphasis now on shifting looking at systems from the bottom up, this notion of adaptive systems and how individuals interact, and why they interact certain ways. Why does somebody move here versus move there? Why does a person do this versus doing something that's more rational? And the whole idea that economics is a rational choice paradigm is sort of, we know that doesn't work, because if people are rational, we would make the decisions that we make today. One way of tackling those types of rational one way of tackling why people make decisions the way they do is this notion of agent-based modeling, the idea of simulating individuals actions of a whole diverse or heterogeneous population, just like the audience here. You guys all come from different backgrounds, you all have different preferences, motivations in life, and so forth. Understanding these diverse agents and seeing what is the resulting system behavior and how this changes over time and how it manifests in various problems. And I didn't know what the audience background was here. So I like to always ask, have you ever seen an agent-based model before? And you know, I can't see the chat. So, but if people, normally when I talk, say, to undergraduates or master students, they've never seen an agent-based model before. But if you watch any of these movies, or you guys in the UK, you get to watch Doctor Who. I'm still 7 seasons behind you. Yeah, this is Doctor Who hasn't been released over here on Amazon, Netflix yet. In these models, in these types of simulations, or in these movies, agent-based models have to replace these large casts of extras, so to speak. So the large fight scenes that you see in Planet of the Apes, or the swarming of the Daleks in Doctor Who, the World War Z, the zombies crawling over the wall in Israel, things like that. These are sort of agent-based models. So a lot of people have seen agent-based models and that might not have known it. Of course, from an academic point of view, we are building models that don't look as fancy as this. Well, some people do actually, like Paul Torrens or NYU does really amazing and very highly detailed agent-based models of pedestrian movement. But the vast majority of us don't really do those types of things. But within agent-based models, what makes them unique is just like in the movie, we have this artificial, it's make-believe, so to speak. In agent-based modeling, we also create an artificial world. We then populate the artificial world with actors or agents. We give these agents rules. So in the Lord of the Rings or fight scenes, for example, it might be, you hit the the elf tackles the ogre or vice versa. While, in an urban setting, it might be something like, Bob buys a house from Jane, right? And we give the agents lots of simple rules. So if a certain condition is met, take an action or do something else. So, for example, if the fire alarm goes off, get up and leave the building. Else, stay here and say, listen to me, keep talking, so to speak. And the idea is we can build models to test different hypotheses or use them as ways of developing the theory. So just to sort of cement what is an agent-based model, I like this simple NetLogo example of agent-based modeling. And the idea is many simple rules applied to many different agents can lead to more complex phenomena emerging. So what you see here are a series of individual cars. These individual cars are the agents in our model. We've assigned them very simple rules. If there is a car ahead of you, you slow down. If there's no car ahead of you, you speed up. That sort of stylized facts. If you drive a car, you don't want to crash into somebody else, otherwise your insurance premiums go up. But you want to get somewhere fast. And what's interesting is in these types of models, we have individuals all going about their own business, but through the individuals interacting with each other, and here in the environment, interacting on the road, for example, traffic jams form. So this is sort of what you see here, where you have the max speed, which is sort of the average speed of the traffic, and then you have the individual red agent here, and you can sort of see how it speeds up, slows down, slows down over time. And the idea of these types of models is simple rules can explain complex phenomena. When we build models, one of the big challenges we have for building models is, can we validate these models against real-world data? Or, are they representative of the system that we're interested in modeling? So this is just a movie from New Scientist, where some Japanese researchers got a car park, put in 22 cars, and made them drive around in a circle. And over time, these cars are driving around in a circle. They were told to drive at a constant speed, but it's very hard to drive at a constant speed unless you're an autonomous vehicle, right? But these cars generate shock waves that you would see in the simple NetLogo model you had before. But the idea of ABM is either build models to test what we do in the real world, like shockwave traffic jams or whatnot, or we can build models for things that we can't necessarily do in the real world. So, for example, we can't really set a building on fire, see how people might react. We would go to jail. Same with respect to COVID. You might be interested in the spread of the disease, and there's been a lot of epidemiological models on the spread of COVID, right? Trying to predict what might happen. And now we have the data to back those models up. So the idea is we build models and to test ideas, explore types of urban phenomena. being GI science here, a lot of the work that we do, and Alison Stahl and her group in Leeds are really great examples of this. We build models linked to the real world, and so we take the world, GI, the world as a series of layers, like people, or infrastructure, physical environment, and this acts as our foundation to our agent-based models, and it allows us to look at the emergence of phenomena like traffic jams, not just in an abstract one array, but in real world space and time types of patterns, and then potentially linked to that. So the idea is, if we went back to the analogy of our artificial world with our agents, we can inform that artificial world with, say, land use data, or traffic patterns. If we want to go from one part of Buffalo to another part of Buffalo, for example, the road infrastructure would give us a routing, and give us where we can drive. We might be interested in how many people live in an area, use population density for that, or other types of things, like other socioeconomic classes that people have. Economic classes might impact your different belief systems, so to speak, or how can we inform decisions or see information through other social information, so we can capture a lot of new data. We can use a lot of data to help build the types of agent-based models, which looking back 10 years ago, when Twitter was just first coming out, people started to use Twitter, it sort of revolutionized how you look at certain types of phenomena. It's really fascinating how we start linking all this type of information together. Just to give a sense of how we can use data, census data, origin destination matrices with respect to where people live, where people work, is one way of trying to sort of build a traffic model. So when I was living in DC, I used to drive out to George Mason campus over here, but every time I would drive around, I would get stuck in traffic jams around the corner. And I was just curious, where do people live, work in this area? So every green area here is somewhere where people live, and then obviously these people get in their car, drive to work. So we can use this origin and destination to work on a simple traffic model type of analogy. And this is sort of what the sort of model looks like. We have agents all trying to get to Tyson's Corner, which is in the center here. We can sort of see the agents moving along. When you see these blobs of agents, that's sort of like a traffic jam type of forming. And the idea is we can use data to help build or inform where our agents start from and where they maybe go to work. But this is like sort of a simple just analogy, and it sort of explains why you have traffic jams, especially around the DC Beltway, which is this sort of area here that you're seeing, sort of a bit like the M25 around London, so to speak. So we've been building models for a long, long time, but now with data that is really sort of changing the landscape of how we can view the world around us. This is enabled through Web 2 types of technologies, especially out of social media. We have lots of new open data initiatives. For example, the Kenyan Open Data Initiative gives you slum locations of all the slums in Kenya, or at least when the slums were mapped there. We have now the Internet of Things, which is giving us a lot of relative information, and that people are contributing geographical information either through the notion of VGI, volunteer geographical information, actively contributing it. People not realizing they're contributing geographical information, this notion of ambient geographical information there. And these new data sources are giving us this new lens to study systems and urban systems as living, breathing social organisms, constant in flux. So the idea, for example, is if you look at, say, who's talking to who on social media, and then we can work out, through geotags on their say tweets, or toponyms being mentioned in places in their tweets. We can get a sense of really how people are talking and communicating, and the connections between people here. And if we can mine this data, especially with data mining techniques, to get new knowledge about the systems that we understand. And then the big question that we've been exploring here is how can we leverage this to better understand how people might perceive the world around them or make decisions, and therefore or potentially inform actions. And I think now with respect to data and we have this new way. It's like sort of constantly getting new sources of data. We have like the traditional data sources we use to study the world around, census data, remote sensing imagery, but we also have this sort of crowdsourced content, this either volunteered geographical information or ambient geographical information. And the question is, how can we start leveraging that to not only better monitor the cities around us, and then analyze what's happening, but how can we use data to help inform models and potentially then ask the models, say, okay, we don't have data on X. Can we then query or better sense or set out ways to actually detect what other types of data is available out there? So, for example, we've been using recently Mapillary and OpenStreetCam data, which is sort of the crowd source of street view imagery data to understand how areas are changing. So if we do some type of deep learning over images, we can detect maybe changes or in an area. So for example, this image of a street view image showed a coffee shop open. This image showed then someone's drove along the street again, and now that shop is closed. So you can sort of do change detection between different imagery there, or we can use street view imagery to build points of interest databases or gazetteers, which could be very useful in countries that don't have formal addresses and so forth. And I'll go through some examples of how we're using social media like Twitter and things like that to help inform our models, and also OpenStreetMap. But the idea is we can use these new sources of data not only to monitor the world around us, but also then to analyze the world and then help infuse into models. And then the big research would be to make the models and query back into the data. But we're still a long way from doing that. Data is giving us a new way of sensing the city, as I mentioned. So, say, if we were looking at urban morphology, the form and function of the city, the form being the physical makeup of the city versus the function is how we sort of use the city. Traditionally we would get information about the form and the physical structure through national mapping data sets like Ordnance Survey maps, or in the US, it'd be Tiger census maps for the road networks, right? But now you've seen the explosion of user-generated content, that of OpenStreetMaps, things like that. We're getting, so we can mine data to understand the form of the city. We can also mine data to understand just the traditional, how people are using the space. Socioeconomic data from the census would be a traditional way of understanding the function of the city, residential area, business area, right? But through location-based social networking and things like that, we can also derive, this is a residential area versus a business area. And I'll give an example of that later on. These sort of explicit examples is also implicit, so mine data. So, for example, mining tweets, for example, to that might not have to actually. So people might be commenting about, this isn't it busy here today, or topics for people to discuss might give a sense of, is this a residential area, commercial area, or whatnot, and it's just amazing how we can mine this data to get a better sense of the cities around us. It's very easy to crowdsource 3D buildings out there now. The OpenStreetMap is giving us a lot of detailed data with respect to roads, points of interest, addresses. I think this is just a screenshot of OpenStreetMap from New York City. One thing I find fascinating about OpenStreetMap is that people choose what to actually label within inside this. So if you look at, say, the Map Cabrera project, in that one, people are mapping the toilets, mapping the water sources, the churches, while here you don't see where people are getting water, but you will see where people are getting coffee. So people are mapping different things, and wonder why people map what they map and why they comment different things. We can also get 3D building height, such as through Microsoft's release of that large repository of 3D buildings, or at least 2.5D types of buildings. So it's very easy to look at physical spaces around us, and we can use topic modeling from social media to understand what people are talking about in different areas. So back in DC, for example, Adams Morgan. So I don't know if any of you went to the AAG a couple of years ago when it was in Washington, DC. But Adams Morgan is just opposite where the AAG was over here. and people go down of modeling for drinking and eating. And if we did topic modeling, what people are talking about in there from, say, social media, we can sort of see people talking about politics, entertainment, some sports, and sort of this light green, sort of like emotional topics like happy, sad, and things like that. If you go down to, say, the White House in DC, where the government and business district is, the conversations down there relate to politics and sports, while educational areas like Georgetown or they talk about educational aspects. So we can get a sense of what people are talking about and what people are feeling in these areas through, say, topic modeling of social media data. Of course, this changes on a potentially on a weekly basis, a daily basis, and things like that. So we get a sense of different neighborhood topics and conversations at this type of thing. Once we had we can expand that type of topic modeling and expand that to large areas. So here we have Singapore, London, New York, Los Angeles, and we can explore different topics and conversations. What's interesting with this type of analysis is we can get topics with respect to, say, education, the blue, and these topics of education relate to universities in, say, California, or business related, or recreation, like theme parks in Singapore. Of course, if I did this study right now, I bet I would have a totally different picture because people now are at home. But this is another thing about this type of data. It's not just giving you sort of the home location or work location. It's giving you a sense of how the whole city is changing and evolving over time. We can look at alignments. So through text mining and through topic modeling and some various things, we can sort of say, these are sort of social media or tweets about people tweeting the entertainment around Broadway. And then we can look at the Broadway area itself, or the theatre district as officially called. And you sort of see a misalignment between where people are talking about entertainment and actually where the official government source of entertainment is. So it gives us this idea of, what's happening in a place and different types of neighborhood configurations one can explore and see in this type of work. We can see how different areas are being portrayed. So these are like words associated with Highline Park, which is a walkway that people in a nice walkway in New York City, an old railway line, versus, say, Madison Square Garden. And we can see different topics emerging, different types of events can be picked up in this analysis, and things. And it gives us an idea of sort of these are the perceptual spaces, and what that really means is this is how people are perceiving the world, or perceiving the world. And we can mine that data, just perceptions of the world around them, not necessarily the authoritative space definition by, say, the New York city government, but more on the space being defined by the people actually there at that time, say through geolocated social media. So that gives a sense of what one can do with these new sources of information. But how can we use this sort of data in our models? We need lots of new sources of spatial data, OpenStreetMap, for example, a lot of near real-time information that we can process to understand what's happening around us. And we have new ways sort of to explore or perceive how people use space in cities. And the big question is, is therefore providing us with new insights into understanding human activity, and can we change these very simple if-else types of rules or the artificial world with these, and embed that with this new source of data. And that's what I want to turn to now in this talk. Initially, this work started with Sarah Wise, who's now at UCL, when we were looking at Haiti. Because when Haiti had the devastating earthquake back in 2010, that killed around 230,000 people, left around 1.5 million people homeless. it was one of the first times that social media, Twitter, usually Haiti, when were generating instant reports about what's happening on the ground. A lot of data was being released on the internet. How can we utilize this data to actually to look at post-disaster relief operations? So this is how to how we can sort of build models using new sources of data. Just to show you Haiti and also the power, I say, OpenStreetMap. This is a map of Haiti pre-earthquake, and the earthquake itself is happening. You see the flashes of light. These flashes of light are basically edits to the map, but you can sort of see how the crowd generated this amazing detailed map of Haiti. Similar examples would have been seen with the Ebola outbreaks in West Africa a couple of years ago. A lot of the crowdsourcing efforts, humanitarian, OpenStreetMap, and various things, were mapping different things, and then different organizations like ITO provide amazing visualizations. The idea is, there's a lot of data out there that we could use to help build a model of potentially disaster relief. The crowd went out and digitized the damage assessment from, say, remote sensed imagery. So red is heavily damaged, green is not so much damaged. And then we have no data issues, which is one of the potential problems. We can use, and then we have the road network, so we digitize from OpenStreetMap. So we know which areas have been impacted. We know what the street networks are like, and we know what the population is through, say, Landscan, which gives us 1 kilometer ambient populations of an area. And then the question is, where would therefore be the best place to place aid centers? So, for example, to, say, maximize the delivery of humanitarian relief during a situation. And therefore particularly relief suffering. So we take this data, we use this population data to instantiate our agents. We give them needs based on the damage. So the more damage it is, the more needs people have. We then want to get the agents to go from their home locations to, say, an aid center. We do that through the road network. And through these types of measures, we can potentially explore where the best is to put aid distribution centers. And so this is sort of an animation of sort of this type of simulation. So we have Haiti underlying is the population. So the more red it is, or pink here, the larger the population. We can experiment where to place aid centers, these blue dots. And the model works very simply. It's a sort of a telephone game, type of thing, word of mouth, which is roughly how aid distribution works in these areas, where an agency will go to a place the day before, like the Red Cross, and they'll say, okay, here's your tickets, we'll be back tomorrow with some aid, come back with your ticket, and you'll get some relief. In this situation, you tell your friend, oh, there's going to be an aid drop, and your friend then tells their friends, and their friends tell their friends, and eventually you have the spread of information here through word of mouth. So when I play the simulation, you'll see these red dots. These are our agents. These agents are finding out about aid distribution, and then they're making the decision. Do I need to go and get food, i.e. aid? And if so, where's the nearest aid center, and how will I move there, i.e. along the sort of the road network? And if there's no road network, what type of terrain will they move over? And through that, we can explore various scenarios. For example, if we place the aid centers here, how would the distribution be? How many people could you potentially provide aid for, and things like that? So this is one example of this using, say, OpenStreetMap data to help inform sort of the spatial environment of our models. We have proliferation of CCTV data now, and pedestrian can use CCTV data to understand people's movement patterns, and there's sort of now mobility data sets out there that find scale, like the Bluetooth sensors or foot count data sets and things like that. Through paths between, say, one entrance to another entrance, we can then extract these paths and then build out sort of movement surfaces across the scene. And then we can use that to help calibrate an agent-based model of, say, movement between one place and another place within the system. So taking that data from this, we can then build a model to work out the probability of an agent entering one door or one part of the scene and next to another. And sort of you can sort of see a heat map being generated over time. We can, and then if the model is not performing as we might expect, we can alter the probabilities within this model to better fit real world data. And you can sort of see here the underlying color is becoming more red. The redder it is, the more frequently the surface is walked as the agent's moving through this scene. And then once we understand how people are using the spatial environment, we can ask questions like, what happens if we put in a block, an entrance here? How will people move through the space? What happens if we put an art installation here? How will people move around this type of thing? And again, we can also test this. So, for example, if we build a model and train the model on a certain time frame of data, and don't use another, and then run the model for out of sample part of the data, how does our model predict the movement pattern for out of sample data? This is an example here. So we might generate, we trained the model on data for 23 hours, but the busiest part of the day we didn't actually use for the model. We ran the model, got the output, and what you see here is basically underestimating and overestimating different places within this scene, and you sort of see a relatively good fit with respect to trying to predict the movement patterns during this time frame. So we can use CCTV data or other types of streaming data set to potentially better understand human movement patterns within these areas. Sarah also looked at the Colorado wildfires using crowdsourced data, especially out of social media data, and how people will perceive threats around them. So there's this notion of social capital in anthropology. The greater your social capital, the better, more resilient you are to disasters, or in times of crisis, you have a larger support network to pull from. And the question is, how can we infuse, how can we pull in social networks and those types of data and use that for agent-based models? So there's a lot of textual data out here. These are just examples of tweets coming from that were captured during this wildfire event, and you can sort of see we can events noted. So it's very easy to use social media for event detection. It's being widely studied. We also get sentiment. Are people happy? Are people sad? Are they indifferent within inside of this? Are they worried? Again, those types of emotions can help potentially impact on how people behave. If you're worried or apprehensive, act differently to if you're calm, for example. We've derived toponyms. So again, I mentioned event detection. So if you're looking at Colorado wildfires, there's a peak of activity happening around this time frame in late June. This is telling us there's something happening in that location. And we know that there's obviously something happening from text, that there's a fire. Waldo Canyon is obviously associated with that fire. What can we do with those types of analysis? One point is we try to delineate the extent of wildfires using social media posts. And that was done through basically GPS, Flickr photos had a precise GPS tag on them. But although the EXIF files that you download, you can get with Flickr photos, have a compass direction inside of that. Most people who upload photos to Flickr tend to have that compass direction. I pull your camera was pointing at when you took the photo off. So we use Twitter to define an area of interest. So we know there's a wildfire happening in Waldo Canyon, and we assume that all people who take photos during that event, and that mentions fire in the tag of the photo, we're talking about the Waldo Canyon fire. We can do some very simple triangulation and try to estimate the extent of the wildfire zone. So this is sort of our interpolation of potentially where the wildfire was during in this event. So this outline is the actual event itself, the wildfire, and this is where the model is predicting there's going to be a wildfire occurring. The reason we're having the model is over predicting sort of the extent of the fire down towards Colorado Springs itself is partly because a lot of the sensors, a lot of people taking photos and contributing information were down in Colorado Springs, so that was pulling the model towards Colorado Spring. We don't do well in the background, and that's partly because there's no one contributing information to there. But it does give an idea that we can roughly delineate some of, at least half of the wildfire area through crowdsourced data. We can use mood to understand, like, are people scared and whatnot. And Sarah Wise then built a simulation model looking at evacuations based on the mood of the crowd and how early warning systems might lead to evacuations happening and so forth. So we can use, again, this sort of data to help to build better types of models, and also look at where bottlenecks are occurring. So if the model is predicting bottlenecks here or here, does the crowdsourced data, say from newspaper reports or Flickr photos, or show traffic jams occurring in these different locations? So we can use crowdsourced data not only to help inform the environment, to help inform the agent behaviors, but also to validate the patterns coming out of the agent-based model. And I think that's quite an interesting thing to do. So just to wrap up this talk, we have lots of new data. This new data is giving us a new lens to study systems. We can mine this data through computational social science methods to really understand the urban environment in details that we couldn't do before. We don't have to just necessarily look at cities from a physical urban form point of view. We can also look at cities from an urban function point of view. We can also, this is the easy part. It's just mapping cities and characterizing what's happening within inside of cities. The challenge is, how do people perceive space, and how do people actually relate to space, and how does that change and evolve over time? And and then of course this notion of connections and social connections within inside of things is sort of giving us a new way of looking at interactions and interaction spaces. And this sort of comes back to this notion of what we've been playing around with, researching with respect to linked spaces. The idea is we might have a spatial neighborhood that can be defined by a city block census tract or a buffer of some kind. We have our social networks, our work networks, our home networks, things like that. But these are all interlinked. Where we are today is very different to where we'll be tomorrow, in the sense our social networks constantly evolving, constantly changing. We get different information from different types of sources, information and things like that. And the idea is this gives us sort of a new way of looking at cities as a living, breathing organism if we utilize new sources of data. This is sort of animation. These are our traditional sort of neighborhoods, these gray areas. But as people move through the city, new networks might be built, new neighborhoods, like new sort of proximate neighborhoods being formed. But things are constantly changing. We can use models and data to explore these changes within cities. And we started building some very simple agent-based models of this to generate sort of very basic patterns of life, where we might have agents located at home. They'll go to work. This is their social network. And you'll see that over time that these agents will interact with each other. They have their home network in red, the work network in red, their home network in blue. So, and you can sort of see interaction occurring. And this simple model, so if you want to know more about this type of stuff, in the book that we did a couple of years last year, has much more detail about the importance of networks and how these systems are evolving. Just to finish, to sort of wrap up, I sort of like whirlwind tour of what I've been exploring the last couple of years. Cities are crucial to our lives, but they're extremely complex systems. we need to, if we were trying to understand cities, we need to understand the social, economic, and physical environments and the interactions of all these different things. There's a lot of interconnections between cities and most with inside of this, but the patterns we see at the macro level emerge from micro level interactions of individuals. Traffic jams form from individuals driving to and from work, for example. Crowds form on streets through people, by individuals going about their daily business. Cities grow by people choosing to decide where they live. CSS provides tools, techniques, a new way of exploring urban dynamics and very fine spatial and temporal skills. But the big challenge in all of this research is really trying to get to the bottom of this, is building models of high fidelity models of human sort of behavior and interactions, and how that plays out over the long run, and how can we calibrate, validate these models using say machine learning methods and so forth. This work wouldn't be possible just with me. There's a whole bunch of people that supported me there, so thank you all. And if I missed anyone, I'm so sorry. Also, I'd like to do a pitch. If there's any master students here or any PhD students here, master students looking for a PhD in any of the stuff I've talked about today, or PhD students want to do a pull in some of these areas, please reach out to me. Otherwise, sort of that's it. And if you want to know more about ABM, there's an excellent textbook that Alison Heppenstall, Nick Mallison, and Ed Manley and myself wrote last year, that has many of the examples that I've shown today in it. So thank you so much for listening, and I'm sorry for going over my 45-minute time. I'll stop there and take questions.
Thanks, Andrew. That was a fascinating overview of the field, and I realized that I read a lot of your papers, but I should read more. So if anybody has questions, please put them in the chat. And so the first one is from Antonia, asking what software do you use for analysis and modeling?
So that's it. So a bit of everything. So for the agent-based modeling, we'll use NetLogo for our prototyping and playing and developing ideas. So that's super simple to use, and that's what we use for the book. Then for large-scale models, we'll use. I used to use Repast, a Java agent-based modeling toolkit, but then I started using Mason, that has more power with respect to linking vector and raster together. So I use Java and Mason for developing my agent-based models. Then going back to like for the analysis, we'll use anything. I mean, I'm agnostic. I'm not a believer in that everything has to be Python based, right? Or open source. So we use ArcGIS. We'll use QGIS. We'll use Python, MATLAB. The whole spectrum of different things, depending on really what works best for us and what's more convenient. Did that answer your question, Antonia? Maybe. So the next one.
Yeah, so the second question is from Alison, and she's asking you what is the biggest challenge that we need to be working on if you can only choose one?
If I can only choose one, that's a terrible, awful question. There's so many. I mean, no, there's this whole notion, right, of machine learning methods, right? And people are developing machine learning methods inside of their agent-based models to do better learning, right? Like decision making. But the problem is, for us, I would argue that just using one method is not necessarily good. So we just recently did a paper where we explored several different machine learning methods on the same model, and how does that impact the outcome? And different methods will impact the outcome differently. So there's but what problem would I work on the most? The problem domain, I think, would be slums and informal settlements, because I really do think that's the hardest challenge. And it's a multifaceted problem, because remote sensing will only get us so far. Every slum is different. So if you use very high resolution satellite imagery, it's great for that slum, but it's very hard to do another one. And so slum classification, there's some advances been done there with respect to object classification of slums and using those objects to train new slum models. Then people living in slums, the alleviation. So I would say informal settlements, but that's not very sexy because there's no research funding in it, which is a problem, you know. So yeah, biggest challenge slums, unfortunately, not enough research money.
And recently, the British government has unfortunately cut a lot of funding in that direction. The next question is from Mahmoud, and he's, sorry, the chat keeps moving. So he's asking whether the research contribution of computational social science is mostly methodological or whether you can think of more theoretical contributions, I guess, broadly to the social sciences.
Yeah. No, so often in CSS, so when we're building the models, and I didn't talk about that in this talk, a lot of our models that we build are grounded on social science theories, and and often we use our models to test theories, like the potentially theory of planned behavior might be one example, or in the disaster situation, the common one would be Maslow's hierarchy of needs. In other models, it'll be various types of theories. So we do build models, but then sometimes there might be no theories there. So a couple of years ago, we were building a model looking at conflict in Sierra Leone, and we were trying to utilize some existing theory on conflict resolution and conflicts themselves. But the theories were not specified enough when we tried to implement them in code. So we tried to, therefore, we had to add to those theories with other ideas that we could pull from the literature to build a better model to capture really what's happening around. So is it methodology or strong? I think it's both. Methodology as well, because you've seen this talk. I don't just use one method. There's a whole bunch of methods in CSS that we use, and that's what it's a bit like in GIScience these days. There's not one single method to solve a problem. There's a whole different ones, but it tends to be grounded in some type of theory.
Great. The next question is about the impact of deep learning and recent AI advances on agent-based modeling, and what do you think of that, whether methods are changing in that direction?
So, as I said, right, there's a lot of interest in deep learning, AI in the agent-based modeling community, right? And I'm going to speak the agent-based modeling first, and then I'll talk about the social, the side of the community, right? In the ABM community, I still think, I'll go back to the quote by Gelman. If you're a pure data scientist and pure just AI guy, you think AI can solve all the world's problems? It can't. There's still lots of AI can never get to the theory. If you use certain algorithms, they might have an algorithmic bias within that. But with that being said, machine learning is used, and Alison, Ed, and myself, Nick, have a chapter coming out this now, which was written last year, on how people are using, and we are using machine learning AI to help work out what are the key parameters that should go into an agent, into a model. How we can use machine learning or AI, what you want to call it, right, inside of the model for better decision making, and then how we can use AI and machine learning to output the results of these models, because these models generate a lot of output. How can we use, say, clustering methods or whatnot to understand really what's coming out of this model? So AI and stuff it has there, but I'm still would like to say it's very important to actually keep it grounded in theory, because if you let the technology drive your application, that's not going to help you too much. Then with respect to the remote sensing, AI is huge. I mentioned with respect to object classification, and then using those objects to train different classifiers onto new objects. The various machine learning methods you use for, say, looking at text or classification of groups, like the Levene clustering method, right? We often use clustering rather than k-means. Why? I don't want to specify it in k-means. You have to specify 10 clusters or whatever clusters, right? But how do we know how many clusters are out there? We can use advances in using the vein clustering method to define that. So it is playing a more important role. Most of my PhD students over the last 2 to 3 years are using machine learning and AI techniques in their various PhDs exploring these various topics. A very long-winded answer to that question. But it's something that I do think about. So yeah.
Excellent. So our time is up, and thanks, Andrew, for an excellent presentation. And also, I thought the discussion was really good. And finally, well, I can plug Andrew's book again on agent-based models. You can find it on all major online stores. And please follow us on Twitter and check out our webinar page. And for some, at least, I hope you'll enjoy the Easter break. Thanks, everyone.
Thank you so much. And if anyone has follow-up questions, feel free to email me, and I'm more than happy to add them on email. Okay. Thank you so much for the invite, by the way.
Thanks, Andrew.
Have a good afternoon.
You too.